Good afternoon, our panelists, Aurélie Carrayol, Philippe Darcis, George Arcangeletti. Thank you very much for your presence and your time. It will be a pleasure to listen your thoughts. Good afternoon, colleagues and attendees of this section of the Rio Pipeline Conference 2021 in this virtual mode. This conference always been a great opportunity to meet friends who work in the industry and sharing the news and updating the common knowledge of our activity. In this section, we are going to discuss pipelines for hydrogen transportation. It's a very important, relevant, and opportunity issue. Probably at this very moment, some of these discussions are being held in Glasgow at COP 2026. Hydrogen combustion is one of the possible solutions to guarantee the curbing of greenhouse gas emissions. So discussions of all the possibilities and difficulties concerning this application need to be addressed, representing a very important matter now and certainly in the years to come. The transmission of hydrogen is a major challenge for developing its use. Certainly, the future of intense hydrogen utilization depends to a large extent on the availability of an infrastructure that can transport and store large quantities while connecting production and consumption. The changes to the existing gas networks will allow for the development of a profitable hydrogen network. A lot of questions tied in with the hydrogen transportation need to be addressed. Is there the possibility of mixing hydrogen with natural gas and existing natural gas infrastructure? In what percentages? Is there a necessity for new standards, innovation, technologies, dedicated equipment for this industry? What are the economics of installing a dedicated infrastructure for hydrogen transportation? A lot of questions, no doubt. Today, in this morning, in the pipeline R&D section of this conference, some of these questions were also addressed by Marion of EPRG and for Cliff Johnson of PRCI. So we can see through all the presentations the big efforts that are being done to guarantee the reliability and safe operations of the hydrogen pipelines. In this section, we will have the opportunity of listening to 3 different speakers from Europe, presenting their experiences, the jobs that are being undertaken, and scenarios for hydrogen pipeline transportation. First, I would like to introduce Aurélie Carrayol to talk to us. Some words about Aurélie. She's a project-oriented woman with more than 20 years experience in energy and a focus on energy infrastructure. Aurélie likes to work in international and multicultural environments. She has had various technical and commercial positions in the gas industry. Now, she is leading the hydrogen projects within the technical division at GRT Gas, one of the major gas transmission operators in Europe. Their objective is to prepare their assets and teams to transport hydrogen through existing gas pipelines in a reliable and safe way. Already, please, the floor is yours.
Thank you very much, Marcello. Good afternoon to everyone. It's an honor to be presenting this afternoon to the Rio Pipeline Conference. So thank you very much for the invitation. So My name is Aurélie Carriol, and I'm working at GRT Gas, which is one of the major transmission operator in Europe, gas transmission operator, with more than 30,000 kilometers of high pressure pipelines. And we transport each year more than 600 terawatt of gas. And we have more than 700 industrial clients that are connected to our network. We are a regulated company, and we are preparing to accept hydrogen either as a blending natural gas with hydrogen or pure hydrogen. So we have two goals, like I said. First one is to integrate the production of synthetic gas or hydrogen into the existing gas network. So synthetic gas, I mean produced by technologies that are using waste to produce synthetic gas, which contains a little percentage of hydrogen, like technology like pure gasification, hydrothermal gasification, methanation. In the French law, there is a right to inject this type of gas, renewable and low carbon gases from hydrogen producers or synthetic gas producers. And we already have had certain about 30 cumulative connection requests to the natural gas network, and we are studying them right now. To define all the procedure to integrate this type of gas at the blending in the natural gas, we have established a consultation working group that is led by GRT Gas, and with all the French gas operators, including distribution, storages, and also associations. And we are working with the clients, because that's a huge topic, to see how the clients are sensitive to hydrogen, even for little percentage of hydrogen. We are defining all the procedures and contract to access to the network, and registry to have a kind of queue line for this project. And we also discuss with the producers through associations, because we need to understand what are their needs, what are their possibilities. Our second goal is to prepare our network to transport pure hydrogen. So we have participated to a huge study that is called European Hydrogen Backbone, that you see on the left side, with more than 20 other TSO in Europe. And as you can see, most of the network can be converted into pure hydrogen by 2040. And we have established that the cost of the transport for 1,000 kilometers would be between 0.11, 0.21 per kilogram of hydrogen. And 69% of the network would be repurposed. And then there will be new construction that are the yellow parts, that are the new pipes. And the objective is really to bring cheap hydrogen, renewable cheap hydrogen produced in the south, for example, in Spain, from solar through electrolysis, up to the main center of consumption, northwest of Europe. And what about France? So we see hydrogen being developed step by step, first in industrial basins. That's the green bubble that you see in France. And we see that there will be a network that will be developed to bring massive quantities of hydrogen for industrial company that will need hydrogen. And it's a cheaper way to bring hydrogen through pipes. And step by step, these pipes will be connected from one industrial basin to another, and then interconnected with other European networks. Yesterday, we just released a study conducted by Guidehouse with other storage and transmission operators that showed that it's very competitive to use gas infrastructure to transport hydrogen, and that the cost will be lower than if we are not using them by 2040. how do we prepare for that? So we are very involved in a project that's a cross-border project with Germany and Luxembourg, which is called Mosaic for Moselle, which is in Lorraine in France, eastern part of France, Saarland in Germany, hydrogen conversion. So this project is with a German distributor called Kreos and a utility from Luxembourg called NCEBO. And the objective is really to develop a hydrogen valley in this eastern part that we call the Grande Région. It's a cross-border region. And to bring hydrogen to big industrial, for example, steel industry, but also mobility in Saarland, because there is a lot of mobility in this area, people going from Germany to France up to Luxembourg. And we are going for the first time to repurpose a 100-kilometer pipeline for pure hydrogen coming from Germany up to France, up to Luxembourg. And this project will be operational in 2026. So here you see the map. It's little. So we have a production from Germany, from Völklingen in the Saarland, from Steag, also production in France, in Carlin, on the other side of the border, from Gazelergie H2V. And we have big clients, for example, Dillinger, which is a steel company that is going to use hydrogen for direct reduction of iron, and also mobility in Luxembourg. And here you see all the pipes that will be repurposed, that are Kreos pipes and GRT gas pipes. And this project belongs to what we call Grande Région Hydrogène. It's a huge initiative with all the producers that I mentioned, the transmission company, and the industry that are using, Dillinger and Saarstahl, but also gas to power industry from Hydrogène de France, which is constructing fuel cells, huge pack of fuel cells, and that will use this large quantity of hydrogen that will be brought by pipes. And here you see all the quantities step by step. By 2026, you have a production from 40,000 tons per year in France up to 5,000 tons per year in Germany, coming to the industrial clients. And 2030, these industrial clients will consume 5,000 tons per year, because its process to produce iron will use more hydrogen step by step for direct iron reduction, like I mentioned. We also are working to prepare our network through a lot of research and innovation projects. We have, which is very rare in Europe, our own research center, which is called RISE, with more than 100 PhDs. And we have demonstrators, Jupiter Mill, and brand new hydrogen test benches called Phoenix, which will be inaugurated November 23rd, so next week, the week after that. So how do we prepare? We have a dedicated research program to first ensure the security and integrity of our assets. So we are going to check our network equipment. We will check our pipelines to be repurposed or to accept hydrogen as blending. We check all the integrity, mechanical integrity. We have a traction machine. We are also involved in safety procedures. We develop a training with our research department because hydrogen is very specific, to know how to manage with the flame that we cannot see by eyes. And we also work on maintaining the quality of transmission. We are working on metering, certification metering for pure hydrogen, management of the network through compression, because it's kind of different than natural gas. It needs more energy for the compression. And we have specific test benches. So we have the power to gas demonstrator in south of France in the Force that I will present later, where we can do real condition test of blends of hydrogen into the gas network. So we are injecting in our network since February 2020, limited amount of hydrogen with 3 clients connected at the end of this network. And we have these brand new test benches in our research center site next to Paris in Alphaville called Phoenix for Future Energy Hydrogen Mix. And we are going to test the tightness of equipment on also all the integrity of the steels with that traction machine that you can see in the picture. And to mention Jupiter Mill. So Jupiter Mill is demonstrator with all the French players, including renewable electricity producers, Compagnie Nationale du Rhône, the electricity transmission operator RTE. We are testing 2 types of electrolysis from McPhee, one alkaline, another one PEM, with the membrane. We are injecting hydrogen into the gas network. We are working also with Terriga, which is the other transmission operators in southwest of France, but that's in GRT gas network. And the other part of Jupiter Mill is methanation. So we are combining CO2 that is captured by le roulotte from industrial fumes. And we are combining with H2 through reactors developed by the company called Keymod with CEA, which is a huge research center in France. And we are producing synthetic methane to inject into the gas network. And here you can see some pictures. So you have on the left the alkaline electrolyzer, the PEM electrolyzer in the middle, and the methanation device that is settled but not operational yet. In injection here you have where the blending is done. It's a little bit small, but you're invited to visit Jupiter Mill. It's open. Also, we received a lot of people to visit Jupiter Mill. And yeah, early 2022, CO2 pipeline would be ready and we will do the methane injection. This project is helped by the European Commission, the South region, our regulators, and also all the people from the area, the city of Aix-Marseille-Provence, as you can see. Then I will focus on our R&D platform called Phoenix. As I said, we have 2 sites at RICE, our research center. This is a collaborative testing facility. That means that we have contracts with other European TSO that will test their pipes and specific steel. We already have running contracts, and it's also open to other companies to test equipments. It's really a European but also international platform, and we would like to be as open as possible. So please feel free to come back to us if you're interested. We are focusing also on gas quality because we changed in GRT Gas our chromatographs to be able to detect hydrogen as a blend into the gas network. We have a strong experience, our research center has a strong experience in industrial safety, and also network materials to test permeation and things like that. And our new benches are really focused on tightness test and pipe integrity, aging of steel tubes, corrosion test, and treatments. And we are also able to qualify meters through aging issues and their performance. So here you can see little pictures of our traction machine and the first test that have been run. This project is also supported by Région Île-de-France. Is funded by also Region and our regulator. And as you can see, that's all what we are going to investigate, the capability and for our pipes to be repurposed and our equipments to accept hydrogen and test also new equipments. These are the international technical collaboration that we have. We are part of Hydrogen Europe. We are answering to call that the ex-FCA-GU that are now Clean Hydrogen for Europe. Our responsible for hydrogen research is leading the strategy topic for hydrogen in GERG, which is a European European research group. We are present also at Marco Gas, which is a pre-standardization group. I'm co-chairing the Hydrogen Task Force. We are part of different initiatives with other TSO, including H2GA, led by SNAM. And we also are very involved in PRCI, especially in the renewable roadmap through our research center with our specialists and experts. Regarding RISE partnerships, here you can see that we have more than 100 PhDs, research center and lab technicians. We have 3 R&D centers. They have 400 patents and innovations, and they are leading expertise in process and gas characterization, pipe and grid equipments, performance and industrial safety, system modelization, and technical economical studies. And here you see all their clients and the collaboration that they have also with European company, but also American company like Energy in Quebec, Edison, SoCalGas in the US, but also institutes like GTI and of course PRCI. And this is the example of all the partnerships that they can do. They can develop R&D roadmaps. They already have answered call to do that. They participate to international research bodies, and they also, like I mentioned, they have expertise and test benches dedicated to hydrogen. Thank you for your attention. This is it for me. So I would be very pleased to answer your questions. Thank you.
Thank you very much, Aurélie. Very interesting to see and to know about all the activities concerning this aspect, all the job that are being done in France, in Europe, concerning this hydrogen infrastructure implementation and also utilization of natural gas existing more. Thank you very much. And so we are going to have the Q and answer at the end of the section. Okay, please. So as the second one that we are going to ask you to present for us their thoughts, this is Mr. Philip Darcy. Philip Darcy, some words about Philip. He received his PhD in mechanical engineering science from the University Blaise Pascal in Clermont-Ferrand, France. Philip joined Tenaris as R&D department manager in Tanza in Mexico. In 2012, he became the pipeline technology senior director in Tenaris, now in Italy. And since 2021, Philip is the chairman of the A2 Pipe DNV GIP, focused on transportation of hydrogen. Philip contributed in more than 100 international technical papers. So we are going to have the opportunity to listen Philip talk a little bit about specifications about also submarine transportation, offshore pipelines. Okay, Philip, please, the floor is yours.
Okay, thank you, Mr. Chairman, and thank you for the opportunity to share this presentation and experience on hydrogen transportation. So I will go through this presentation that will give you an overview of what we are doing and also the global trends that we are seeing. Just a few words before about Tenaris. So Tenaris is it's a pipe solution company that deliver pipeline or line pipe and pipeline services to the industry. Okay, so let's move forward to the first presentation. I would like to start from probably a higher level already presentation, just looking to the booming demand of hydrogen in the world. As you know, the hydrogen will be part of the energy transition that the world is facing, and there are different ways to present this. what I like to see and to share with you today is how the energy or the hydrogen will gain momentum in different sector that we are seeing in this graph, because we will see that in the next decades that hydrogen will be part of our everyday life. So from this graph, I will try to put the pointer here. So from this graph, you can see that at the end of the day, the needs of using and producing and transporting hydrogen is not new. Okay, in the past decade, hydrogen demand were looking and targeting mainly ammoniac production and other chemical processes and also refineries. But the hydrogen as part of the decarbonization plan that every country and the entire world has will gain momentum, especially in what is called the hard to abate sectors that mainly are looking to heavy industry like manufacturing and iron ore reduction, and also heavy duty transportation as road, maritime, and aviation. And we expect for 2050 that the hydrogen will take an important part of this energy for this sector, around 15–20%. What we can see also from this graph is that the energy, the hydrogen demand will double almost by a factor of 2 every decade. Now, let's have a look of how it will look like. So for this, I like to use this illustration from the DNV, in which you can see in blue an actual network of natural gas, and in green, sorry, how the pipeline hydrogen network will look like. So if you look, the blue one is well known and is well quite classical. You see that we start from the extraction of natural gas. So for here, for instance, you have extraction from an offshore field. You will have go through the processes, and the natural gas will be used in different of application like power generation, industrial, residential, and commercial. Concerning the hydrogen, the first step will be to produce it. So there are different ways to produce hydrogen, but the trend is to use what we call the blue hydrogen or the green hydrogen. Concerning the blue hydrogen, we will use natural gas, and through a reforming technology, we will generate hydrogen and also CO2 that we will sequestrate. On the other hand, we can also generate through electrolyze green hydrogen from renewable, from electricity generated by renewable that could come from offshore wind farms, or also onshore wind energy or solar energy. This new hydrogen generation, we will need a dedicated new high pressure hydrogen transportation system, and also a repurposed of a local grid and existing transportation in which probably it will be blind at the beginning. Now, let's look at two different examples, one from the onshore and one from the offshore. Concerning the onshore, and already mentioned this in the previous presentation, the most ambitious example that we have is the so-called European Hydrogen Backbone project, in which you can see here that different countries in Western Europe will aim to transport hydrogen in existing and in new pipeline. Here you have some numbers to see how big this project will be. So here we are talking of around 40,000 kilometers of pipeline, in which 31% will be brand new. that represents 5.2 million tons of pipe, and 69% will be repurposed. If we look now to another example, here, this time looking to the offshore hydrogen pipeline transportation. Here, a good example is the use of wind farms. So here you have two illustrations that represent at the end the same process. So we will generate offshore through wind farm electricity. This electricity through electrolyze will be converted in hydrogen, and this hydrogen will be then stored on offshore through a container that will be directly on the seabed, and after that exported through a pipeline to the shore. The main challenge of such project is probably the intermittence of the energy, the electrical energy that is produced due to the intermittence of the wind strength, and also the intermittence of the demand of hydrogen. So here, in such system, we will have important fluctuation of the hydrogen storage and transportation that will challenge different limit states or structural integrity scenario of the pipeline. If we can name, for instance, the fatigue that will be important to do the pressure and unpressure of the line. Now, let's review the key elements in the development of hydrogen pipeline. Here, I listed 5 main key elements that need to be addressed. The first one is the transport capacity. So the question is how much energy is moved. As you know, if we compare to natural gas, hydrogen has a much lower density, but has at the same time a higher heating value. And for a similar volume or for a similar energy to be transported through pipeline, we will need 3 times more volume of hydrogen rather than natural gas. So how we will deal with this change of energy value and density in the future, it's a question that the industry needs to face. The second question that we may have is concerning the safety of the hydrogen itself. That is different from natural gas. The hydrogen has, for instance, a wider inflammability range, and then also a lower ignition energy. So this higher explosive nature of the hydrogen need to be faced from a safety perspective. The third key elements that need to be addressed is the structural challenges related to material degradation to the presence of hydrogen. So what need to be modified? The third key elements that need to be addressed is from an operative perspective is how is the pipeline integrity program affected, what to inspect for. And finally, the last one is the conversion of existing pipeline into hydrogen. What will be the key challenge? What modification, if any, of the existing grid that we have need to be performed in order to carry out 100% hydrogen or a blend of a certain percentage of hydrogen. So these are the key elements that we see and that need to be addressed. Now, if we look to the different surveys that were performed in the industry through different professionals, we can see that here a good example that is from a survey made in January 2021, in which we asked to around 600 professionals the following question: what is, in your opinion, the most significant barrier in adding hydrogen to the gas grid? And here you can see that 1/3 of the answer was linking to a lack of guidelines or standards. And the second one was linking to safety. That is probably linked also to lack of guidelines on standard. So here it's clear that something is still missing in the industry concerning hydrogen pipeline transportation. And we need to have a critical, I will say, a look on what standards are existing and what need to be done in order to answer to these two industrial preoccupations. So if now you look to the actual way of designing hydrogen pipeline, we can easily observe that the main code of reference is the ASME B3112, okay, entitled Hydrogen Piping and Pipeline. Here we can highlight three main facts concerning this code. Code is that in one hand is very conservative, mainly if we use the method A as design reference, that will lead to a restrictive grade in terms of pipeline and also to limited safety, to very severe safety factor. The other remark that we can make is that this code is mainly based on the limit state based on burst, so linking to the hoop stress. The second point that we can say is that this standard does not consider all the design limit state that onshore and offshore pipeline may face. An example is the third-party damage. We can also mention soil movement or typical fatigue load. On the other hand, we can also observe that this code does not provide guidelines for offshore pipeline. So here, based on this observation, we can see that the new hydrogen pipeline guideline is needed. Now, let's have a reflection of how we can build this kind of guideline or standard. And here, I will say the basic statement is to try to identify the potential scenario and failure mode of the pipe, and is to assess them through an evaluation of in one hand of the demand, and on the other hand of the resistance or the strength. So for this, we can evaluate these different aspects. Okay, in one hand, what type of loading the pipe will have. Okay, here we can see the typical three categories that we have: that pressure, environmental, and functional, operational. From this type of loading, we can evaluate the type of failure. Like for instance, for pressure, we can identify burst, collapse, and running crack. We can identify how to assess it. So instance here is strength and fracture. And after that, we will arrive to the material characterization. Okay, so it's how to evaluate the pipe material. If we do
please,
yes?
Just 1 minute more, please.
Possible? Okay, so here, concerning the environmental, we are in terms of type of failure, we are speaking of fatigue in elastic regime, fatigue, and for functional operational, ice plateau deformation. And here, we have all the material characterization that here need to be done in order to evaluate the strength of the material. And the big question mark is how to evaluate it. and if the experience that we have in other environment are valid in hydrogen environment as well. Here, this is an example of guideline that is currently in the industry. There are different ones. Here, the one that I take as example is the DNV GIP H2 pipe that aim to provide guideline based on the DNV STF 101. So the guideline will be a supplementary recommendation based on this standard and aim to provide guidelines for safe and reliable design, requalification, construction, and operation of pipeline intended for transport of hydrogen. Today, there are 22 participants, and here there is a scope of work. I will just ending with this conclusion. I think that hydrogen transportation through pipeline is a key element in the energy transition. Hydrogen will affect important things that need to be addressed, like how the pipeline is operated, the safety picture, risk assessment, and the design of new and requalification of existing pipeline. And for this, a new hydrogen pipeline guideline is needed. And I will end here. Thank you.
Okay, Philip, thank you very much for your thoughts. We could see what you talk about, a present list of questions that need to be answered, need to be addressed to guarantee the safety of these operations. And we are needing guidelines, we are needing work more in a lot of aspects. No? So let's move to our third speech. We are going to ask for Mr. Giorgio Arcangeletti, some words of his history. Giorgio, after the achievement of a master's degree in mechanical engineering in 2005, joined Saipem in 2009 as system engineer, mainly involved on subsea equipment engineering for several executive projects. In 2016, he started working as technical manager for innovation projects and development activities also for external clients. Since 2020, Giorgio is leading the R&D engineering within offshore facilities and pipeline business units of Saipem. Okay, Giorgio, please, the floor is yours.
Yeah, thank you very much. I'm trying to share the screen. Hope you can see my presentation. Very good.
Okay.
Is that okay? Very good. So thanks for the introduction, Marcelo, and thanks for the opportunity to speak here. Just a few words about Saipem. So Saipem is a global EPCI contractor in the oil and gas infrastructure, but also new energy sector. And starting from 2020, Saipem Offshore division launched a program to advance technologies for H2 offshore transportation. So basically part of the topic we are facing today, because we are very focused, I'm very focused on offshore transportation of hydrogen. And in this presentation, I will explain to the audience and list to the audience all the design challenges and the opportunities we see for our future pipeline systems. Okay, so we will start from a brief introduction, and then we will go discipline by discipline to see the gaps that we identified during the activity and the way we achieved the first results. As you have seen from the introductory slide from the cover, there are many co-authors on this work. All the discipline basically normally involved in a pipeline design here in Saipem have been also involved in this task. So mechanical design, material technology, structural integrity, flow assurance, and safety engineering are part of the team working on this subject. We will go through a brief explanation of how we redefined our technological and innovation roadmap to target innovation and advancing in technology, and then we'll move to the conclusions. So, as already partially, let's say, explained by the speakers today, there is a lot of increase in demand in hydrogen pipeline. At least it is predicted and envisaged. For example, the International Energy Agency see that pipelines for hydrogen transportation, both reconverted or brand new, will increase of about 8 times respect to the numbers that we had on 2016, and this is a great target to take. So we launched this activity to basically to cover both new pipeline and existing pipeline engineering. We started from a phased approach. So we basically completed for the first part of the job, the state of art. Then we identified the gap and we list the gaps, technological gaps, and we redefined the technological roadmaps and we implemented the technological roadmap. We are in that phase. All the discipline involved, as we said, so there is no need to repeat all of them, but basically the fluids that we are targeting are obviously hydrogen, pure hydrogen, or a blend of hydrogen with natural gas. This slide summarizes basically the value proposition that is behind our effort on this task. So basically, we want to advance knowledge on hydrogen effects on materials and weld, and we will see how. We want to promote and support the standardization to ensure a fit for purpose and a safe offshore pipeline design. We don't want to have a reference standard that are too much over conservative. I mean, we want to encourage operator and investor to take decisions. So we want to encourage the production of a good standard, not over conservative. Design for transport flexibility. This is an activity that a target that can be achieved when you know well the thermodynamics of the fluids that you have to deal with. Our other target is to develop a method in structural integrity analysis, and this is particularly important for repurposing of aged pipelines, previously working with natural gas, for example. We want to ensure a safe by design offshore pipeline system and enable a better and safer use of existing offshore pipeline. And this can be done through a good risk assessment and identification of the threat and quantification of the consequences. We will see how later on. I move to the next one. Covered by Philippe. We are part of the same team in the JP he mentioned, so we are very aligned on that. A good way to approach this problem is through a design based on limit states, and this is aligned with what the DNV STF 101 already does. So we started from that. Because failure modes, generally speaking, may be affected by the presence of hydrogen, and these should be taken in consideration. We need to find the correlation between the limit states, the failure mode, the peak loads that the pipeline see during the installation operating life, and so on, and the material subject to hydrogen effects. On the other hand, we have another standard that is available, the SMB 31.12, that appear to be a bit constraining when it comes to hydrogen, for example. We will see a practical example in the next slide. And so we cannot rely only on this standard, which is more applicable for onshore transportation than for offshore transportation. So given this, we adopted a stepwise approach to fill that gaps. So we started from the analysis of how hydrogen affects failure modes and material welding properties. We defined a testing matrix, so a material testing requirements for hydrogen environment. This one, okay, this one was already discussed by Philippe. So basically, we grouped the failure modes by limit states. And so you see that we considered all the failure modes, basically starting from bursting, going to fatigue. And we tried to associate a type of loading to each failure mode and to, let's say, assess the design activities that needs to correlate this failure mode with the materials and the hydrogen environments. So at the end of the story, the exercise gave us as a return the proposed test in H2 environment. So we have a list of tests that we will perform. We are already starting to perform on pipes, and like this, we will have results that will give us very precious, very valuable information about how hydrogen affects the material at different conditions, at different percentage, and partial pressures. And this is the same approach that was discussed with DNV within the H2 pipe JAP. So as we mentioned before, let's take a very practical example. We have an existing pipeline with natural gas. We want to repurpose this pipeline for hydrogen, okay? And we apply ESME BTORI 1.12, section A. So we see that, okay, in this graph, the column in orange represents different wall thickness for the same of different diameters, okay? But in all cases, you see that the system design pressure that is allowed with natural gas is not the same that is allowed for hydrogen in case of repurposing of the pipeline when you apply ESME BTORI 1.12. Because the pressure for hydrogen for the repurposing of the pipeline is the green line. So you see that is very far below the starting point. I mean, when it comes to offshore, for sure, it's not easy to deal with something like this. I mean, it will have an impact on wall thicknesses, and so on the weight of the pipe, and so on the installation feasibility and the associated cost of the system. So definitely, we cannot only rely on this very poor exercise. When it comes to requalification, we should also take in consideration integrity assessment of the actual status of the pipe, and then we need to make a prognostic assessment of the future integrity. At the same time, if the pipeline has to be reused with hydrogen or a blend of hydrogen and natural gas, we need also to evaluate the fragile fracture and fatigue limit states. In terms of materials, okay, in terms of materials, we have different areas that are impacted by hydrogen. So hydrogen basically impacts all the key material properties. So starting from the ductility, toughness, fatigue performances, in particular on the circumferential welds, that are the welds that we normally perform on the firing line of our vessels. So not easy. H2 diffuses through virgin surface. We may need to improve the internal surface condition and to reduce as much as possible the stress concentration factors. But this should be considered, but it should be not a limit in the feasibility of a system. I mean, because we need also to find a way to have let's say a break-even, or at least a compromise between this and what a normal standard manufacturing process can give to you. Then, okay, but evaluation of root open defects and use of welding technology is a key factor also for the evaluation of repurposing of an existing pipeline, because when it comes to repurposing, you need to identify also the allowable defects that are, let's say, compatible with hydrogen, and to move on like this to avoid any issue in the future. So definitely ESME 31.12 should be complemented and modified with additional consideration of testing criteria, or at least we need a complement to DNV STF 101 to make offshore pipeline definitely more easy to make for hydrogen. So structural integrity is obviously one of the key points of the R&D activities. Here you can see that we basically set up an assessment of on a large diameter pipeline, and this analysis and the activity behind allowed us to produce a dedicated procedure to assess the allowable defects for an existing pipeline that we want to reconvert for hydrogen use. Flow assurance, we partially already covered this item. So with hydrogen, we have, and with hydrogen mixed with natural gas, we had a different phase envelope, not easy, not symmetric. So we need to face with it. And also hydrogen, for its properties, has a different energy carrying capacity than natural gas, we already mentioned. So we made a sensitivity on a 26-inch pipeline, for example. You can see that if we pass from 0% of hydrogen to 100% of hydrogen, keeping constant the energy carrying capacity, we should increase the flow rate of about 70%. And if our target was to keep the pressure losses constant, we would never achieve the same energy capacity. So we are obliged to accept a lower capacity in terms of energy by the system.
Excuse George.
Yes, please.
Just 1 minute more, please.
Yes, I'm closing with safety. Safety is a key actor here because in case of accident, there are measures hazard associated to a release of hydrogen. So buoyant stability of passing ship, flammable clouds above sea level, impact on subsea and atmospheric environment. We want to consider all these things, and we want to produce a system that is low risk. But at the same time, I mean, there are some gaps and no experience offshore, no available data, no collection of statistical database. We need to build that. We need to build this, I think, all together. I mean, with the contribution of partners and operators and contractors. So we will then, for safety, start from the identification of hazard and threats, the quantification of the frequency of loss of containment, and the assessment of the consequence. And then we will be able to produce a real quantitative risk evaluation. We are in a good progress on this. So this is the roadmap of my team for the future. We will continue insisting on offshore pipeline design activity with our standardization contribution with H2 pipe on H2 pipe JP. We will improve our construction welding capabilities and installation methods. For material technology, we will go through testing, real testing, full and small scale, and the methodology and models for structural integrity. On safety, we will continue the activity that I just mentioned, and the flow assurance, we will deeply analyze the dynamic behavior of hydrogen with natural gas blends. So definitely we need innovation to advance on this and to make it economically feasible. We need an effort, especially on design, material welding, testing, to correlate design and material properties and failure modes, as we say. Industry cooperation is key here. And okay, that's how we reassessed our technological roadmap to meet that. So this was the last. Thank you very much for your patience and attention, and thanks to the team and the contributors to this work for their passion and involvement on this. Thank you very much.
Okay, thank you very much, George. A very good presentation, very exciting, showing all the aspects that we need to be taken into consideration. I'd like to very much. Unfortunately, I don't have time for questions. Unfortunately, I would like to thank you very much for all your contributions. Already extremely well contributions. Philip Darcy is very good. George, perfect. A lot of worries, a lot of job need to be done, considering everything that you have exposed to us. I think that questions about design, about capacity, questions of how to fund everything of these huge investments to be done. So I think that's the exciting time to come that everybody need to go home to a lot of job to be done. Okay, thank you very much. It was a beautiful presentation. It's nice to talk to all of you. Excuse for not having time for any questions. Okay, thank you very much.
Bye.
Thank
See
you.
Thank you.
Thank you.
Bye.